In physics, we often refer to momentum when analyzing collisions. This is because unlike energy, which can be lost in a collision due to sound and heat depending on the situation, momentum is always conserved. There are three types of collisions: explosions, elastic, and inelastic. For elastic collisions, it's best to picture the objects bumping into each other. Here, we have two tennis balls. Since after the collision the balls separate and return to two parts, the initial momentum of the system is divided between the two. It's also important to remember that momentum is a vector quantity, so be sure to keep the vertical and horizontal components in mind when analyzing situations such as this. For inelastic collisions, the colliding objects stick together after making contact, affecting the mass of the system and therefore the momentum. Here we have two railroad cars running along a track to reduce friction. Since the mass of the system is increased on impact and momentum is conserved, the result is a decrease in the velocity of the system.
Hi, I'm Alex, and this is Gavin. I'm talking because he can't, and according to him, I don't shut up. So, we are here to talk about impulse. Dun-dun-dun. Now, impulse is the change in momentum. For some reason, it is measured with a J. Momentum is with a P. We don't know why, but whoever invented it won't tell us. So, as we know, momentum is mass times velocity. Therefore, the change in momentum is mass times the change in velocity. So, therefore, once again, impulse with a J, we don't know why, is equal to the mass times the change in velocity. And if you do it this way, mass times V initial, V final minus V initial. So the final velocity minus the initial velocity times m, get your impulse. And then we'll cut. Okay, another neat trick about impulse is that it is also equal to the force applied to an object times the time that the force is applied. So, using the other equation, we also know that because impulse is equal to momentum, the change in momentum is equal to the force times the time. So m delta v is equal to ft. If you do some funky little math and divide by t, then you get the m delta v over the time is equal to the force applied. So if you get rid of all those unnecessary variables like the mass and velocity that nobody cares about, what you're left is that 1 over the time is proportional to the force applied, which means that as the time you apply a force to an object goes up, the force that the object feels goes down. Okay, impulse with the force and time is the way catcher's mitt works, because as the ball hits it, see how this is a lot thinner than this one is? Okay, the catcher's glove. With this, when the ball hits it, there's no time between when it hits the edge of the glove and when it really gets into that pocket and starts to hurt your hand. The catcher's glove, when it hits the pocket, has enough time, it has to go through all this padding just to get to the pocket so you can catch it and so it doesn't hurt your hand. That's the way it works, because as the time that the force of the ball is applied to the glove increases because there's more time, more padding, the force that your hand feels inside it decreases. This is what happens when a catcher does not use a catcher's glove. And then we'll cut it.
Watch the speed of the two pitches here. The faster pitch has a higher impulse because of the force of the pitch required to make the ball accelerate so much. Also, changing the gloves changes the impulse because there is more time for the baseball to slow down with the thicker catcher's mitt than the skinny fielder's mitt.